students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can try to help you in whatever way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will review powers and roots today. Yay! For the last few videos, we have been discussing commonly used measures of variability. We've discussed range and interquartile range. Before we start working with the last two measures of variability, I want to take a little bit of time and discuss some basics about powers and roots, because they're going to be important once we start to calculate variance and standard deviation. So as we discuss powers, there's a little bit of vocabulary that I want us to discuss just so that we're all clear on what we're talking about. So consider this example right here. This whole thing is called a power. The 2 in this example is called the base, and the exponent is the number that kind of floats up and to the right of the base. The exponent represents how many times the base is used as a factor. You've probably seen exponents at some point in your life. So for example, here we have 4 times 4 times 4 times 4. And if you recall, sometimes this little dot is used for multiplication. So another way of writing 4 times 4 times 4 times 4 is 4 to the 4th power. 4 is the base in this situation, and 4 is also the exponent, as it turns out, in this situation, because 4 has been multiplied against itself 4 times. Here, let's look at the letter D. Just like here we had the base of 4, here we have the base of D. So D times D times D times D times D is the same as saying D to the 5th power. Again, D is the base and 5 is the exponent. Here we have -6 as the base. So -6 times -6 times -6 is the same as -6 to the 3rd power. -6 is the factor that's used 3 times in this example. Here we've got 5 times 5. So 5 times 5 is the same as 5 to the 2nd power. Another way we can say 5 to the 2nd power is 5 squared. 2 identifies how many times 5 was used as a factor. So 5 was multiplied by 5 twice. So let's do a couple more just to make sure that we're all talking about the same thing. Here we have x times x times x times x times x. That's the same as saying that you have the factor of x, which is the base, and it was used 5 times. The factor was used 5 times, and so 5 is the exponent. Here's the same thing. D times D times D. D is the base, and 3 is the exponent, saying that the base D was used as a factor 3 times. Now, another way that people refer to this 3 is a cube. So whenever 3 is used as an exponent, you could say that the factor was cubed. So in this instance, another way that you might hear this is D cubed. Same thing here. If we were looking at just this final product here, you can see that -3 was used as a factor 4 times. So -3 to the 4th power is equivalent to -3 times -3 times -3 times -3. Here we have 7 squared, or 7 to the 2nd power, saying that the base 7 was used as a factor twice. So 7 times 7 is the same as 7 squared. With variance and standard deviation, we work with squares and square roots specifically. So I want to look at those in a little bit more detail. So first, let's look at the squares. Here we have 2 squared. And if you look at it in more detail in terms of an area model where it's covering space, you can see that this square right here has the dimensions of 2 squares width and 2 squares height or length, right? You've got a height and a width, or a length and a width, that has the same dimensions, 2 times 2, and that's why we get 4. We get 1, 2, 3, 4s, and that shape is a square. So the factors describe the width and the length, and the 4 describes the area. The same thing is happening here with 3 squared. Here we have another square. The length of this square is 3, and the width of the square is 3. And so the area, everything inside the square, can be seen as an area of 9. Same thing is happening here. The width of the square is 4, and the height or the length of the width is 4. So here we have 4 times 4, and we get 16. Okay, so this 16 describes all this area. One of these 4s describes the width, and the other one describes the height or the length, or whatever you want to, however you want to describe these squares. Now let's discuss the vocabulary associated with roots. To discuss roots, there's 2 major features that you should be aware of. If you had this symbol almost looks kind of like a check mark with this long line at the top of the check mark. This is called a radical sign. So you could say that you can refer to this as radical 9. Another feature is sometimes the radical sign will not have anything on this little tiny shelf. Can you see this little tiny shelf right here? When that tiny little shelf is blank, there's nothing there, you should assume that it's a 2, it's a square root. If other numbers appear here on the shelf, then that will give you the name of the root. So if you have a 3, it could be considered a cube root or a third root. If you have a 4, it could be a fourth root. So that's kind of how you read this number, this feature. Every square root has a principal square root, and that is a non-negative square root. For the purpose of our class, you should assume that all values underneath the radical are positive, and we will be just working with the principal square root. Okay, so we're just going to be working with the non-negative square root in our scenarios. So as we're working with the radicals, I want you to look at the information that's given, and I really want you to think about prime numbers in the factorization process, because I think it's going to be key into understanding what's okay. So here I have a height of 2 and a width of 2. 2 times 2, or length times width, gives me an area. In this case, I get 2 times 2, so the length is equal to the width, and I get an area of 4, okay? Here is my area, 4, and I want to find the sides. What is the length of the sides? What number, when multiplied by itself, will give me the area of 4? Well, if I take 4 and I break it down into primes, 2 times 2 times 1, then because there is this little tiny 2 or invisible 2 that sits on this little sill right here, this little shelf, then I can take out this pair of 2's outside of the radical. The 1 stays inside, and I basically get 2 radical 1, right, which is just 1, and I get 2 times 1 is 2. Okay, this gives me the sides, the length of the sides, or the width of the side. Okay, and this gives me the area. Here, this is the side, and this is a side, multiplied by one another, and I get the area. What it's doing, it's the same thing that's happening in this situation here. What makes this situation special is that you're actually dealing with the shape of a square, not any other type of rectangle. So you're dealing with a special shape of the square. So let's look at a situation like this one, something that you might find obvious. Here is the area is 100, and the radical is saying what number times itself will give me the area of 100, right? So that I can make this perfect square. Well, there's a couple ways you can look at this, but I'm going to break it down into something that just gets really minute. So let's look at the number 100. What are some ways that I can make 100? Well, I can make 100 by, let's just say 50 times 2. Okay? Is 2 a prime number? Can I get the product of 2 through any other way except multiplying 2 times 1? No, I can't, so 2 is a prime number. Let's keep factoring 50. How can I get 50? I can get 50 as 2 times 25. Okay? Is 2 a prime number? Yes, we already decided 2 was a prime number, so we've already decided that. 25 is not a prime number. I can break down 25 even further, and I can break down 25 into 5 times 5. Is 5 a prime number? Yes. Is 5 a prime number? Yes. So I can say that 100 is the same as saying 2 times 2 times 5 times 5 times 1. Okay? Remember, we have this little 2 sitting on this ledge, so I can actually find pairs, like pairs, and take them outside of the radical, because that's what the radical is telling me to do. It's saying, what are the numbers multiplied times one another so that I can find what the sides are to this square that has 100 little units inside of it. So I would get 2 times 5 times radical 1. It's a weird radical. And 2 times 5 is 10 times radical 1, and that's the same as 10. So I can say that when I have something that has a height of 10 and a width of 10, I'm going to get this perfect square. Not that I can draw it, but that's what it's supposed to look like, okay? So I would get this perfect square. Let's see if I can somehow make this square a little bit better, okay? There's 100 squares inside, the length is 10, and the width is 10 here, okay? So these distances here are equal. I get a perfect square with 100 units inside. Let's look at a situation where it's not obvious. Let's look at a situation where I get 75, okay? I want to take the square root of 75. I have a square, perfectly shaped square. There's 75 units inside of it. I want to know, what are these lengths? Don't know these lengths, but I know that they have to be equal. All right, so let's take the square root of 75. How can I make 75 using prime numbers? Well, I can make 75 as 25 times 3. Is 3 a prime number? Yes, it is. You can only get 3 by... Is 25 a prime number? No, it's not. I can make 25 using 5 times 5. Is 5 a prime number? Yes. Okay, so another way that I can write this is radical 5 times 5 times 3 times 1. Now, since this is a square root, it's looking for like pairs. So here's a like 5, but everything else doesn't have a pair. So I can take this pair outside of the radical, but everything inside doesn't have something that can be taken out. So I have 5 radical 3 is the square root of 75. And what does this mean? It means that this length is 5 radical 3, and this length is 5 radical 3. And I can even prove it to you using my Google calculator, right? Because I should have 5 radical 3 squared should give me 75. So let's go here. I've got 5 radical 3 equals times itself equals, I get 75, right? So what did it do? It found the square roots here. So it went from the area to the lengths of the sides that were equal. Let's return to this slide again. Here we have 2 times 2, a length of 2 for each side. The width is 2 and the height is 2. 2 times 2 is 4. There are 4 units inside. If I took the 4 units, right, if I had 4 and I wanted to find the sides of the lengths so that the sides were equal to one another, I would take the square root of 4 and it would give me the length is 2 and this length is 2, so that's the same as 2 squared. Same thing's happening here. If I have a 9 and I want to take the square root of 9, I'm saying if I have 9 units and those 9 units make a perfect square, the shape of a square, what is the length of each side if those sides were equal? Because in a square, the sides are equal. So for that situation, this length would be 3. See, 1, 2, 3. This height would be 3. 1, 2, 3. And my area would be 9. In this area model, we see that the area is 16. If I want to know what the sides are of this square, because in a square the sides are equal length, then I would want to take the square root of 16 and get that the sides are 4. Each one of them are 4, and 4 squared gives you 16. So see how they're kind of like flip-flopping back and forth? Squares are the inverse of square roots, and square roots are the inverse of squares. So there's just inverse functions that you can go back and forth between. We're going to need this idea of going from a square, right, which takes up area, and a side, which just is a distance or a line, in variance and standard deviation. So what's the big idea? Today's big idea is that squares and square roots are inverse functions. They undo each other. Squares describe the area of the square, okay? The area that the square is taken up, the units that are within. The square roots describe the lengths of the sides, the equal lengths of the sides. So if you want to take the square root of a number, what you're ultimately trying to do, saying that if there were a square, a figure of a square, that had the area of that number that you want to take the square root of, you want to know what is the length of each side for that particular square. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher, Taurus, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!